No, sir.
No. But I press share and why it's not being seen?
Now it's visible, sir.
Now it's okay. We'll go through it again. You mean to say you did all of this without that slide? Because you don't know what is unit 1, what is unit 2.
So that's what I was wondering, like, how am I supposed to understand this?
Yeah, I pressed it, but somehow that slide, without the slide, we can't make out anything. Anyway, let us go. So just read that previous slide. That is what I was discussing initially. That's what I meant. So essentially, I just paraphrased it in my own words, but basically, I don't know of any commercial process I said which involves only one process unit. That's in first line. Then he says one or more reactors are present. Yes. And then there are units for mixing, of course. Heating and cooling, I gave you the example of evaporation and condensation. Then he says separating products. Of course, otherwise, how will you, I mean, normally you are doing is to extract one product out of number of them. So there has to be some separating chamber or operation, right? Let us say we had only one product was desired, the others were undesired, they would constitute impurities. But in the balance, those impurities have to be accounted for, right? Because your separator may not work at 100% efficiency. Suppose I have a cyclone separator for separating particles, and let us say that particle is able to separate anything above a mean particle size of x micron, n micron, but nonetheless, it will have some particles, it will have a distribution, right? So we need to worry about, so it's not that it's 100% and everything above a size of n micron is separated and everything else which is smaller is discharged. It's never like that, right? So the discharge stream will also have some larger particles, not just the fine particles below the cutoff. So in the mass balance, we have to worry about, let's say, 20% of them, of the larger particles that are going with the fine particles below the size n microns. Am I clear? Is it understandable what I mean? So the mass balance has to include those, right? You cannot just say, if I am balancing particles above n microns, I can't say I'm just going to neglect that 20%. Then what this slide also tells you is removing potentially hazardous pollutants. So I use the word toxic. There could be a toxic element, and I can't let that accumulate. As I keep operating that plant, the concentration in a stream of this toxic compound will rise. So I have to find ways to keep it within a cap, within a limit. And we are not reached, I said we are not going to do that today, but that is something that we would like to take up towards the end of this month, before the end of this month. So then he said, before we analyze it further, let us take a look at what is a system is. But I defined what the system is. I said, whatever we draw the boundary about is our system. And if I have many units, I can have multiple boundaries. So that is what we can see with the next slide. There are two units, 1 and 2 he has called them. Could be reactor and separator. You have one product from unit 1, some product from unit 2, and something intermediate also. So I said you can draw the dashed line about any system, complete system of composed of all the units, or you can also draw them about each unit. So that will then be a subsystem boundary. That is a subsystem boundary. Suppose I look at the outermost rectangle in this figure. The main point I made just a few minutes ago is that I don't need to worry about any streams which are inside this boundary. What do we mean by that? That means, essence is we only need to consider in the overall balance those streams of feed or product, in this case, which are intersecting that overall boundary. समझ गए? Whatever is not intersecting that boundary will not be a term in the overall balance. All internal streams will have its own balance within the box, but since it's not intersecting, feed 1 is intersecting, we have to consider. Feed 2 is intersecting the outermost boundary, we have to worry about it, etc. Product 3, yes. But anything that is inside, like at points B or C or D or E, is immaterial as far as this outermost system boundary is concerned. So what this diagram shows is that the definition of system and subsystem is up to us. So we can have a boundary about unit 1, which is subsystem 1. We can have a boundary about dashed line about unit 2, the square around unit 2 in system 2, subsystem 2. So that's 3 types of boundaries. But you can also have a boundary at point B, which is not any equipment or any process unit, but it is indeed a mixing point, right? I mean, you have a composite feed which is going into unit 1. So that is a summation of the feed which is fresh, which is outside the system boundary, which is feed 1. And to that you are adding feed 2. The composite stream is the total entering unit 1. So we can also have a balance at point B, which is, you can say, the mixing point, right? Similarly, you can have a balance about point D, where a product is siphoned off. So you had something coming out from reactor unit 1, then you siphoned off product 2, and only a part of the remaining was entering unit 2. So there are 5 such units out here. Overall, then one about unit 1, one about unit 2, one at the mixing point, one at the product siphoning point D. Obviously, the more the number of units, the more the different types of balances I can write, because I can combine different units together. So for instance, if I had 5 units, I can have unit 1 and 2 together, 1, 2 and 3 together, and soon the matter becomes very complex. And we cannot do it manually. But up to 2 units is very much doable, right? Now, the question for you is, what sort of balances can you write around each of these dashed rectangles? I only told you you need to worry about the streams which are intersecting the rectangle. For instance, for unit 1, that would be the stream after B, then product 1 and the stream C. But now, how many different types of balances can you write for each rectangle? Well, you can definitely do an overall mass balance for each of those rectangles. And if it's a non-reactive system, you can do a component balance for a two-component system. If it's a two-component system. If it's a three-component system, you can do two-component balances which are independent and along with the overall balance. So you can do a species balance and as well as an overall balance is what the point I wanted to make. Of course, how you make the balances, in what order, and how you label them, all that depends on you because you have to draw the flow sheet. And different people can choose different symbols, different bases, etc. That's why I suggested if the flow rates are given, just choose those flow rates. So these are the type of 2-unit balances that we are able to do within a 1-hour exam. As I said, beyond that, I'll give you an example. It becomes much harder to do in a limited time. Okay, so those are the principles. What you can do is you can try to sketch such a diagram for an actual problem. So here is a 2-unit diagram process. Diagram of a 2-unit process. Not a specifics are not given, they're just called A and B. It's just for our illustration. They have already labeled what is known and they have asked you to find flow rates and compositions of the unknown streams. So just like the previous diagram, like so, can you now tell what are all the balances that can be done, and can you draw such a diagram with the dashed lines around it? So of course you will always have one overall balance to draw the boundary of the overall system. Since it's a 2 units, so we can always draw about the units. So draw those boundaries.
So in this, one more thing we can do is like we can split the one and two into two different arrows instead of one single arrow.
Right, of course. So you can have a balance about the splitting point, right?
Yeah. So we'll have like three balances. Like first around the first box, from that we'll get the one. Then around the imaginary box, from that we get the two, and from the second box we get the three.
But can we actually do as you are saying?
So because in the first box, like since it's a continuous steady state process, so there's no accumulation. So
Right.
the balance should be like whatever the input is, like the 100 kg per hour, and output is going in like two different directions. One is going up and one is
So what
going
you're saying
outside.
is the flow rate will be just 100 minus 40.
So not exactly like, so the yeah, that like we have to balance both the products A and B, right?
No, overall flow rate.
Yeah, actually, yeah.
Overall flow rate.
Yeah, overall flow rate will be 100 minus 40, that is 60, and the mass percentages we can find like from the balance of A and B.
Component balances. Yeah, of course
Yeah.
you can do that. Actually, this this question straightforwardly gives you M1 dot or Q1, whatever you label them. Because just like you said, but many times I would say it may be better to first start with an overall balance. In this case, as you said, you can start with balance with unit 1. But you can also do the overall balance. Suppose you were to sketch the rectangle enclosing both the squares, just as the previous one. Why not? Then what is the unknown stream?
So the stream 1 and 2 won't even count in
Won't
that
be
case.
right.
Only
But the
3
bottom
will.
stream will count, no? The 30
Yeah,
kg.
the bottom stream will count, and
What is the
like
only unknown?
yeah, the known streams and the stream 3 will count, so we can find stream 3 directly from that.
Exactly. So you have already found stream 1 and you have found stream 3. In this case, the order also does not matter in this particular problem.
So I had a doubt, sir, if this sort of a question comes in the exam, so do we have to follow a specific procedure, or like we can like go about it in any way we want?
Any way you want, because this time online exam, it's very difficult to because if you have a proper one, maybe someday maybe next time I'll give you an actual flow sheet. I'm not saying I'll ask this thing in the exam, but a real large flow sheet like we had to do, I mean, I had taken various humidification problems and urea plant problem. I mean, there are 100 flow of reactors and urea prill towers and whatnot and combustors and I mean, there is no way you can check where the error is. So it will have to be an objective type where all different answers are given and you choose it. And obviously, if you in 1 hour, if you are just given 1 or 2 questions, you should be able to solve them correctly. And otherwise, the marking scheme we already discussed 50%, and then beyond that, right?
Yeah.
So, because one thing, I mean, this is only the second time I taught that course, and the first time I just gave something which people found, मुझे 1 घंटे में solve ही नहीं होता. I didn't anticipate. The problem is this basic exam, you want as long as you choose the right answer or out of the whatever thing you get. Otherwise, it's only half the marks. But that's all right. Half the marks you are not going to get every time, right? You're only going to get if you get it wrong. If you get it correctly beyond that, and then it's anyway relative grading this time, so there's no difficulty, right? The minors, majors, but the base is 50%, and then you go to 100% if you have it right. So you can do it pretty much as you want. I mean, all I'm saying is it will be very hard to check who went wrong where. I mean, last time I got into that protracted discussion with every student, I definitely am not going to do that any of that this time. Because then they, these days, unlike our time, they don't accept no for an answer. They keep coming back, mera ye mark, mera wo mark. And I mean, at my stage in life, I'm least bothered about marks, unlike you guys, right? We are at different stages of our life. So I don't want to get into protracted discussion. If your answer is not correct, then and I'll give you sufficient time. I mean, I'm not going to give long things like last time. You'll have sufficient time. You'll get 50% if the answer is wrong. Otherwise, you get 100%. So that's it. And that's it. And a calculation course, that is all right. Because it's impossible. And then somebody says, I got it on the last step. So give me partial marks. I mean, So all these rules are we have laid out from before, because I cannot keep discussing with all the students, especially online. It's too difficult. So you pretty much you can do what you want. In this case, it doesn't matter how you do it. So first write the overall balance. It's a good idea. So you just said you will get the overall stream M3. So 100 coming in, 30 also coming in, 130, 70 going. So 130 minus 70. So that is also 60 kilogram per hour. You can also do an overall balance for one of the two species, A or B. Why not? Why don't you try that? But first you should just label the diagram. So M3 dot, M1 dot, M2 dot, or Q1, Q2, Q3, which is the notation I prefer. So actually that's already done. So that's really what it is looking like, right? So you need to find M2 dot, M3 dot, and the corresponding x's or mass fractions. So what I said is, just like you now did the overall balance and got M3 dot as 60 kilogram per hour by the balance about the outermost rectangle. Similarly, I said do another balance for A or B. Perhaps A, because you have short symbol there. So how much of A is fed into unit 1?
So 50 kgs per hour.
Correct, 100 into 0.5, wonderful. So similarly, something is going in the upstream of unit 1. Find out how much is going.
36.
36, 40 into 0.9, very nice. But some A is also coming at the mixing point.
So 9 kgs.
Correct, 30 into 0.3, very good. And now similarly, something going out from unit 2.
18.
30 into 0.6.
18.
18. And what about the overall unit?
So overall the input is 59 and the output is 54.
Right, so M3 dot you calculate as 60. So 60 x3 is what is coming out, no, for A?
Yeah, and out of that 5 kgs is A, so that's like 8.33%.
Right, so the only unknown is what? X3 here, right?
Yeah.
We'll find it.
So 0.0833.
Very good.
So then
So
we get 1 minus x3
the
as
balance gave us M3 dot. The overall component balance of one of them gave us x3, and of course 1 minus x3 because it's not independent. Now similarly work out, you already worked out M1 dot by balancing about unit 1. You just told me it's 60 kilogram per hour.
yeah.
Similarly, find the component, find the A by a similar balance, because if it overall balance is working, component will also work about the first unit. Hundred into 0.5 of A was coming in, 40 into 0.9 is going out, and 60 into x1 is the immediate output of unit 1. find the unknown.
So x1 will be 0.233.
0.233 because that's the only unknown. So now once you know m1 dot x1 dot, you can do overall balance about the mixer.
Yeah.
So 60 was there, 30 is there, so m2 dot is known.
So for the exams, we'll get similar sorts of questions.
I don't know, exam is still far away. November sometime, right?
Yeah.
By October end, we'll finish mass balance, then we have to go to energy balance. Then some problems on combined mass energy and biological. That's about all we will. And we will do non-reactive plus reactive. So both we are doing reactions. And you know, once you have more than one reaction, the problems become somewhat trickier. So longer, I would say. Anyway, this is the first of the double unit thing. But as I said, इस पर हम कई सारे variations डाल सकते हैं. There's no end to the permutations you can do. Rather combinations that you can do. So let us see how they follow overall balance first or right. So overall balance we just found out to be 60 exactly, and then overall mass balance on the species, that makes a lot of sense. That's what we just got as 0.0833. Perfect. So zero point 0.5 into 100 was in the first stream, then 0.3 into 30, etc., etc., etc. And the only unknown was x3. Then balance unit 1, you just did 60 kilogram per hour. That was the first balance that you did. Similarly, the balance for one of the components about unit 1, that gave us 0.233 because x1 was the only unknown there. So that's very logical. And then the mixing point m2 dot, you just got 60 because 60 plus 30, so 90. And then you did a component balance for one of the components, and that's the last unknown that you have. So in a way, what we have done is the simplest type of double unit balance. So of course, things can never be this simple. I mean, this is just a bit too straightforward. Maybe next time, next Monday, I'll take an example which is kind of very hard to do, and I don't think we want to do it because say multiple units, and then we want to go to then stick to 2 units, I think. Otherwise, no 1 hour, it will be very hard to solve. So let us take an example where the balances are not as simple as this and straightforward, everything one gets coupled to the other and we have to solve them simultaneously. And then let us go to double unit, but let us stick to double unit, not more than 2 units. And then let us add some recycle or pulse streams to it. And that's a very, very common problem in continuous processes. So then the matter becomes somewhat more challenging, and yet I think it's a problem that one can do within an hour. So essentially what we started with the simplest one balance, one reactor or 1 unit case, and then we saw how to do it systematically. Obviously, if you have to write for everything, all those 9 steps, it will just take too much time, but a lot of them you can do mentally. But you can follow that overall process that we delineated last time. Now we applied that to the whole same concept of a system to 2 units in series. and you saw how to actually do the overall balance. The only thing here is the overall balance. We only worry about the intersecting streams. So that's why we could simplify things. Whatever happens inside is immaterial to us. That was the new concept here, right? And that is, I think, a very useful concept in analyzing any large system. So now let us take some other more complicated examples just to show that it's not something that we can do in half an hour. And then let us take up some other problems which we can do within an hour. But let us add more streams or more complications or more feedback or feed-forward loops to what we discussed today. Okay, so on this line, we will start next week. Okay, and some next week is more interesting, so at least you guys will not get bored. Okay. All right, we continue and we'll keep doing this in all of October.
Thank you, sir.
Thank you very much. Thanks.